project involves some work that we've done here in Tasmania under the Smart Irrigation for Profit project, where we're looking at the application of irrigation water to pastures under pivots in particular. And down here in Tasmania, working with a team of people from here and also some from the National Centre for Engineering and Agriculture, we've been looking at increasing farm profit through efficient use of irrigation input to dairy pastures. And we've looked at 5 different sites over a period of 3 years across North and Northwest Tasmania. 4 of those sites we've been working with the farmers to improve irrigation, and 1 of those sites we've been focusing on automation. That's particularly with the National Centre for Engineering and Agriculture, using a platform called VeryWise. If we look at the way in which we approach this work, in the first year we spent quite a bit of time just monitoring farmers' use of water and collecting data so that we could understand what practices were occurring, and we had no feedback or interaction with the farmers themselves, just the collection of data. In the second year we started to provide some information back to the farmers to help them to make decisions around their irrigation and improve their irrigation. But in the third year we've actually been interacting in a very detailed way with farmers, where we've been talking to them every week and advising them on what we believe they should be doing, just so we could see whether there was an improvement in their ability to irrigate efficiently. So that's the process that we've used across our 5 sites. Now, what we feel is really important is the power of data. If you're not measuring and monitoring, then it's very hard to understand what's happening and then to make changes. So we felt it was important to go out there and to monitor what was happening. So we put a whole heap of sensors out there. We put soil moisture sensors in the ground. We used weather stations. We measured their power and their water use. And as a result of that, we were able to understand not only what their inputs were in the system, but then doing weekly walks of the pasture, we were able to get a measure of their pasture growth rates as well, and we're able to combine that information. So that's I suppose, the power of data, and that's the process that we went down for these particular sites. So in this talk here, we want to think a little bit about the right amount of water, and we're going to think about the concept of readily available water and evapotranspiration. We're going to think about the application at the right time, particularly the system capacity and what the impact of that has on how often you irrigate and in the right place. And we're going to think a little bit about variable rate irrigation, all to optimise growth rates and improve productivity and profitability. So I'm going to hand over to Mark to talk about the right amount.
So in Tasmania, we tend to like to think about our soils as being a giant sponge. Now for us, our normal root depth is somewhere around about 300 millimetres. It'll vary where you are. In Tasmania, it's fairly shallow because we have very high levels of aluminium and manganese in our soil, and that tends to be released once the soils become acidic at depth, and so roots generally don't push down much further than 300 millimetres, and in fact most hover around about the 200 millimetre level. So if you think of that level or that piece of soil as being a sponge, if you fill a sponge up with water, water flows out the bottom, and that's exactly what happens in your soil. If you fill your soil up with water, lots of rainfall, lots of irrigation, water will start to flow out of the bottom of the soil, that section you're looking at, the root section. If you leave it for a couple of days, it'll actually stop running, exactly as it would with a sponge. Once you stop pouring water in the top, water stops flowing out the bottom. If you squeeze the sponge, you can still get water out of it. And it's the same principle with soil. If roots extract water from the soil, which is a bit like squeezing only in reverse, you end up with less water. Eventually, if you let the soil sit in the hot sun for ages, it'll dry out completely. But we're not interested in that part of it. We're interested in the bit of soil that's known as the readily available water, which is a bit between being that point where it stops running out, so it's at filled capacity, it's totally loaded with water, but it's not losing any, and where plants begin to struggle to actually take up water. They can take water up once they begin to struggle, which on the thing here is known as the refill point. That's where a plant will begin to struggle to obtain water from the soil. It can get water right down to the wilting point, which is this point here, but we don't want it to be in that area, because if the soil dries out to this area, plants are struggling, and the first thing they do when they start to struggle is stop growing. If you get down into this area, plants actually senesce or die. So what we're trying to do with our readily available water concept is fill it up to full capacity, which is here, and then draw down to the refill point and operate in this zone, and that's known as the readily available water zone. How much water do soils hold? Well, it depends on your type of soil. So if you have a sandy soil, and sand basically means you've got large particles. In very crude terms, soils are either sandy or clayey or a mixture of the two. Clay means very fine particles, sand means very coarse particles. If you have coarse particles, you can't hang on to a lot of water, because water doesn't get absorbed inside the particle, it actually sticks to the outsides of particles. So the more particles you have, the more water you can hang on to, which is why clay soils have a higher water holding content than does sandy soils. So you can see per millimetre you get 0.3 millimetres of soil per centimetre of depth, or 10 mils in sand. If you go down to, say, the clay loams here, you can hold 8 millimetres per centimetre. And so it really depends on the type of soil you have, how much water you can hold in that top root zone, which once again is dependent on how far your roots can push down. If we take the farms and members of this project, and we have Cressy, Montana C, Rocky Cape, South Riana, you can see the important figure over here is the readily available water in the 30 centimetre root zone, and you can see it varies between the various locations. We range from 19 at Cressy down to 44 here at Rocky Cape, 42 on the, which is the other site, and on a clay loam it's down to about 25. On average in Tasmania, somewhere between 20 and 30 is pretty much the normal for most of the soil types.
So if we think about one of our sites down at Cressy, where we've done quite a bit of work, under that one pivot there are a number of different soil types and rooting depth of our pasture. So if we look at the diagram that we have in front of us, right up the top of the pivot where we dug some pits, we noted that the rooting depth was down to about 40 centimetres, which means that on this particular site, where we have about 19 millimetres of readily available water in the 30 centimetre root zone, for this particular area of the pivot, there is about 25 millimetres of available water for those plants to grow. If we look down in the middle of the pivot, in a slightly wetter area, we had about 19 millimetres. If we go right down to the bottom of the pivot, where the rooting depth was only down at about 15 centimetres, then the readily available water is only about 10 millimetres. So there's only about 10 millimetres of water available for plant growth before you then have to replace that with some more as it goes out of the system. So it's really important to understand your rooting depth and to understand the size of the bucket which holds the water that the plants can grow in. So if you think of the situation where you have a mixed species of pasture, for instance, up in New South Wales, you want to think about the pasture species that has the smallest rooting depth, because that's going to dictate the size of your bucket for being as efficient as possible in growing your pastures. So if it's a clover-based pasture and it's only down at 20 centimetres, then you really need to be working on a 20 centimetre bucket in terms of the amount of water that's available. It varies depending on the soil type and the rooting depth, as you can see. So if we just think about what we've just gone through, we've talked about how much water is available for the plants to be able to grow. What we want to also think about is how much water is going out of that bucket every day, and that's the concept of evapotranspiration. So here in Tasmania, evapotranspiration at its peak in January, it was up at around between 6 and 7 millimetres of water that is disappearing every day as the pasture grows, and over winter it's less than 1. Those figures could be higher in areas of New South Wales. It could be 10 millimetres or more. So you've got to think about what is the maximum amount of water that can disappear from your system. So the bucket can hold a certain amount, but there's a certain amount disappearing every day. And so typically here in the middle of summer we'd be losing something like between 35 and 50 millimetres of water over a week. And we need to think about the impact of that in terms of replacing that water that's being used. Now, if we think about the third thing that I believe is really important in understanding how to irrigate effectively, it's not just how deep is your bucket, so how much water is there that your roots can use and your pasture can grow with. It's not just the amount of water that's disappearing every day, the evapotranspiration, but it's also your system capacity. So in terms of how regularly you need to irrigate, that will depend upon the system capacity. So the system capacity is the maximum possible rate at which a machine can apply water to the irrigated field area, and it's expressed in millimetres per day. And so if we think about a hard hose, for instance, where we're putting on maybe 30 millimetres on an area and it takes 6 days to go through the total area that you're irrigating before you get back onto that first application. If we think about 30 millimetres, 6 days, the system capacity for that scenario is 5 millimetres per day. So we've got the capability of putting 5 millimetres per day equivalent into that system. And so that will determine how well you can water with regard to how much is disappearing out of the system. If we think of a pivot that puts on, say, 12 millimetres in a 48-hour period, which would be typical of a lot of our bigger pivots down here, that system has a system capacity of 6 millimetres per day. So it's 12 millimetres. We then calculate that down to 24 hours. That'll be 6 millimetres per day. So that's the system capacity, and it's really important to understand that. So if we think of a situation where we have a system capacity of 6 millimetres and we have evapotranspiration of 6 millimetres per day, that would mean that we would need to be irrigating that site every day to be able to replace what is going out. So our actual scheduling would need to be a scheduling where we were applying water every day. If we think of another scenario where we have a system capacity of 6 millimetres per day, evapotranspiration of only 4 millimetres, then in that situation we'd need to irrigate 2 days on and 1 day off to be able to replace what is disappearing from the system. If we have a system capacity of 12 millimetres and evapotranspiration of 6 millimetres, we'd need to irrigate every second day to be able to keep up with keeping the bucket full. And finally, a system capacity of 12 mils but an evapotranspiration of only 4, we'd only need to irrigate every third day. So you can see understanding the readily available water is really important, how much is available there, understanding how much is disappearing and understanding your system capacity really helps you to understand how often you need to schedule your irrigation to make sure you're replacing what is being used. If we just pull all those concepts together, let's assume a situation where we have a rooting depth that gives us 24 millimetres of readily available water. We have 6.5 millimetres of evapotranspiration. The system capacity is 6.5 millimetres, so we can replace 6.5 millimetres as a maximum. And we're going to water every third day. So at the beginning of this scenario, we're at field capacity. So we start off here with a water budget. We're at field capacity, the blue line here. We don't water for 3 days, so we basically have 2 days off, and then the third day we turn the irrigator on and we water. And so what we've done is we've dropped down to a deficit of minus 13. We then irrigate for a day, and the 6.5 mils going in, but 6.5 mils also going out. We then don't water for 2 days here, and then on the third day we water again, and we're now at a point where our deficit is below 25 millimetres. And then we stop watering again for 2 days, and then we turn the pivot on and we say, wow, everything's really dry here, we better leave it on the whole time. The big problem then is that we're putting 6.5 mils in, which is the capacity of our system, but we're also losing 6.5 mils. So the amount of water is way down below the refill point. It's at this deficit. And that's the big problem that we see on so many pivot irrigation systems down here in Tasmania. The soil is allowed to dry out, the system is then put on, but we're not able to replace what is going out and bring that water back up into the readily available zone. And so we get what is termed, or what we've termed, the green drought scenario. So having put that theory together, let's think about an example of what has happened here on one of our sites down at Cressy, and how irrigation scheduling has affected crop productivity. And I'm going to start by handing over to Mark.
So one of the most important things about irrigation is actually starting at the right time. So we conducted some research 25 years ago that looked at this problem, and we determined that if you started 7 days late, so if you were just only 7 days late starting, which is very common in irrigation, you can end up going at least below 60% below full production for at least 40 days, regardless of how much water you poured on after that 7 days. That delay caused at least a 60% drop in production for a minimum of 40 days. Now, we've actually turned around and modelled that, and the modelling suggests that if for every day you are late in starting up irrigation, you will lose 105 kilograms of dry matter a hectare over the entire season. So if you assume an irrigated area, fairly common size here, 50 hectare pivot, and you're 5 days late starting, then you will lose approximately 26 tonnes across that pivot area for that whole season, which is a substantial amount of money. Oops. And so I'm now going to hand over back to James, who will actually tell you a real example of this.
So if the modelling suggests that for those delays we're losing productivity, we've got an example here in South Riana that we monitored in 2016, where we started off at about 80 kilos of dry matter per hectare per day in growth rate as we came into early summer from spring. And then on that season it was very dry, so they ran out of water from one dam and they had to transfer to another, and they had a 9-day delay in getting irrigation back on again. And so the water in the soil dropped below the readily available zone, the plant started to stress out. After that 9 days they started irrigating again, and then they got some rain, but it took quite a period of time, right through from the beginning of January to about the middle of February before we started to see pasture production getting back up again. And so during that period of time there was about 50 to 60 tonnes of dry matter that was lost, and that was only as a result of a 9-day delay. So we can certainly see that 105 kilos per hectare per day's delay for a pivot situation can be easily identified as being a situation that we can see. So a big loss as a result of only 9 days delay. So just going to the Cressy side and thinking a little bit about what has happened down there. On this particular farm, in the first year that we were monitoring, they only grew between 30 and 40 kilos of dry matter per hectare per day, even though under that pivot they applied 6.2 megalitres per hectare of irrigation through that season. So they were putting a lot of irrigation water in, but they were only getting very poor growth. So we monitored that in the first year and said, well, what's going on here? Why are they using so much water but they're not actually getting good growth? And so what we did is we had a look at a water budget for, and this is an example here for February, where we have the number of irrigations up the top here. We've got our readily available water zone in the green here, and we're just measuring the amount of water that's going in and out of the system. So we had a big rain event at the end of January that filled the profile right up, and then we had a period of time where water was being taken out of the system, so within a day or so of that rain event. And then there was an irrigation, so water went back into the system. We then didn't irrigate for quite a period of time, so water's going out of the system, and then it's back into the system again. And so what you'll see is that the soil here, the soil moisture depth is dropping down below the refill point, which is at the bottom of this green zone. And what we do is we get to this point where we're irrigating, but when we're irrigating, we're not actually wetting the profile up so that it's back in the readily available water zone. So we're putting irrigation water in, but but we're not getting a response in growth because the plants aren't going to be able to easily use that because it is below that readily available zone. And so that's a situation in which water is going into the system, but it is not leading to optimum growth. And so that's what is seen as an explanation for the poor production in that first year. In the second year, we managed to start off at about 80 kilos of dry matter per hectare per day, and then we dropped right down and then managed to get it back up again. Now the question is, why has this occurred? And one of the issues with this particular site was that under a big pivot he was cutting silage on a number of paddocks, and so he stopped watering adequately to be able to keep the water in the readily available zone because he had to stop while he did these silage cuts. And as a result of that, the pivot dried out too much. And it was only in January, when all that had finished and some of the other issues had been sorted out, that we managed to get his production back up to 80 kilos of dry matter per hectare per day. And so if you look at the soil moisture probes, the soil moisture probes show that the site was drying out considerably over that period of time where there wasn't adequate irrigation. If we look at an example of a water budget for that particular year, here's a big rain event. We didn't water for quite a period of time afterwards. The applications here, so the irrigation is the blue lines here, and then the green lines are some rainfall events. But what you'll see is that after that rain event, the soil was allowed to dry right down, and then even though they've begun irrigating and they've irrigated for quite a considerable period of time, what we see, and sorry about that, is that all the watering that occurred from about November through to towards the end of December wasn't applied where the roots were able to readily use that water. So it was way down below the readily available zone and it wasn't lifting it back up. And so all of that water was not able to lead to efficient pasture growth. So we dropped from 83 kilos of dry matter down to 43, and then only in December, when we had 2 irrigation events followed by 2 rain events, we were able to lift it back up and start pasture growth rate occurring again. So we can certainly see the impact of scheduling, and particularly startup after a rain event in this case, having an impact on pasture growth rates. In the current year, the 17-18 year, we've been monitoring pasture growth rates, and you can certainly see that we've started the season really well at 100 kilos of dry matter per hectare per day. We've dropped down to about 60 when there was some maturity coming in, but we've certainly kept pasture growth rates going really well, back up to close to 100, and then we dropped down right at the end of the season. There was some armyworms came in and had an impact. We only used in this particular season up to the end of February 4.6 megs per hectare of water compared with 6.1 megs per hectare in the first year. Now if we put all that together and summarise it, what you'll notice is that for this particular site in the first year, he used 6.2 megs per hectare of irrigation, an average growth rate of only 34 kilos per hectare per day, compared with where we've now got to in 17-18, which is 74 kilos per hectare per day, and only at this point, by the end of February, 4.6 megalitres per hectare of irrigation actually has been used. So you can certainly see the massive improvement in growth rates and in the water use efficiencies as a result of being able to use water and apply it for the plants to be able to grow effectively. And if we think about some figures on that, so comparing the first year with the last year, there's been an opportunity loss of about 40 kilos of dry matter per hectare per day in that first year. If you think of the pivot that was under, that's about 420 tonnes of pasture over 3 months. And if we think of the extra cost of feed to purchase to fill the gap, then that's over $80,000 of extra cost over those 3 months in that first year. And so certainly you can see that if you don't get it right, it costs you a lot of money. So the summary is we've got to beware of the green drought. We need to make sure we start up right at the beginning of the season and we start up right after rain events in particular so that we keep the water in the readily available zone. We need to make sure we keep the bucket topped up. That's the key. So our scheduling is got to be such that we don't allow it to dry down. Poor watering costs money, and this start-up time at the beginning of the season after rain is something we need to really make sure we get right. So just moving on quickly to variable rate irrigation, putting the water where we need it. Why variable rate? Well, variable rate is important to enable us to manage variability due to management and infrastructure. It could also be used to be able to manage variability due to our management and infrastructure. It could also be used to be able to manage variability due to our soils and our topography. So we've already shown that on a particular site we could have big differences in our readily available water across that site. How do you manage that? And variable rate irrigation is one way that you can manage it. But in particular, the first advantage that we see from variable rate is the ability to be able to manage due to things like different crops under the same pivot. So you might have a lucerne crop under one area of a pivot, you might have a pasture crop or a mixed pasture crop somewhere else, just a kikuyu somewhere else. You might be cutting for silage under another part of the pivot. If you've got those scenarios, if you've got variable rate, you can apply different amounts of water to those different parts of the pivot using the variable rate technology. If we think of how variable rate works, we certainly need a map that can represent all the variability that's there. And we've shown that by putting together maps that we can save about 30-odd%. So at Cressy, a 34% reduction in irrigation, which is about 2 megs per hectare, has been saved as a result of using variable rate, where we're only applying the amount of water that we think we need in the different zones. If we go to another site at Montana where we've put in a different map, we've had 29% reduction in irrigation, or about 1.4 megs per hectare, or 70 megs over the season is what we can potentially save using variable rate irrigation. But how do we go about identifying these prescription maps to be able to put into the system to be able to do variable rate? Well, first of all, you need to understand the variability of your soil. So an EM38 map is often very useful to identify those major soil differences in the zones. You can use topography and the way in which the ground changes in topography to identify what we call wetness index. And so there's a number of different ways of trying to identify the variability that exists under a pivot. But the most important thing is to make sure that variability is representative of the issues that you face on your particular pivot. And I think what we like to think about is the fact that a farmer knows about things like the very wet zones and the dry zones under a paddock, and can identify those quite well. If it was possible to go out there and to identify those by walking a pivot and maybe drawing a polygon around the area on a map that is wet versus an area that is dry, if you can take that information and put that back into a prescription map, and an example here is the inclusion of field observations and roads and a waterway, and if we can put those down to 0 water, then we can really more effectively utilise this pivot, making sure it's not getting bogged in these wet areas, not wasting water in these zones where it doesn't need it. And so putting that information onto the map is really important. So we gather all the information together and we put it into a final map for VRI control, and that's what we use to be able to manage our zones. And I think in the situation in New South Wales where you might have different crops under different areas of the pivot, being able to identify those is really, really important, and produce them on a map to put into a pivot is certainly going to potentially be beneficial. If we think about the value of VRI, we find down here that usually the value of VRI, apart from managing different zones like different crops, is often at the beginning of the season. Here is an example of our Montana site where early in the season, in one part of the pivot, things dried out really, really quickly, whereas in another part of the pivot, things were quite wet for a period of time. So you'd be putting more water on here and you're putting less on here. But as the season goes on, both those areas respond quite similar, because you're correcting the problem that occurs, and then the plants are using a certain amount of water at both of those sites, and so you're just watering according to the amount of evapotranspiration or the amount of water use in that system. So you need your VRI early in the season. You don't necessarily need to use it later in the season. So you've got to think about the change in variability through a season if you're using VRI, and for us, very often the value is in the start of the season. In terms of payback, and we need to think about that. There's an investment in VRI. What do we need to achieve to be able to make sure that we pay back that investment? Well, the very important thing that we see when we've done some work on this is that we need to get improved productivity. So if we can improve our production by 1 tonne of dry matter per hectare, and we certainly saw that at Cressy over those 3 years, then our payback can be down as little as 3 years. If all we're doing is saving water and not getting any more growth, then it could be more than 9 years that it takes to be able to pay back that investment in VRI. So improved production is really important. Can we expect improved production due to VRI technology? Well, that depends on the variability of the site and your management of that site, the sorts of things you're doing on that site. So you need to be able to determine that. So the summary we come to there is we need to ground truth variability maps to make sure that they make sense. VRI can save water. VRI zone management changes through the season, and VRI payback depends on growing more pasture or growing and utilising more pasture. So that's just a quick overview of some of the learnings that we've had from this site. We certainly need to acknowledge the Australian government through the Rural R&D for Profit Fund, TIA and Dairy Australia for putting money in, and in this case, as a recording, the New South Wales government, the local land services in the Hunter region, the National Centre for Engineering and Ag for their input as well.